So for our sample problem on reversible reactions, we have this particular problem which in terms of stoichiometry cannot be classified either as a first order reversible or a second order reversible reaction, primarily because the coefficient of the species here on the left side is 1, and here on the right side you have 2. So it cannot be falling on any of the two pre-derived working equations for first order and second order reversible reactions. So we will have to set up our own rate equation here and other necessary equations based on stoichiometry so that we can answer this particular problem. Now, in here, you have dinitrogen tetraoxide converted to nitrogen dioxide. So it's a reversible gas phase decomposition. This is to be carried out at a constant temperature. Your feed consists of pure dinitrogen tetraoxide at 340 Kelvin and 202.6 kilopascal. Your equilibrium constant, K sub C, or capital K sub C, at the temperature of 340 Kelvin is 0.1 mole per decimeter cube. So calculate the equilibrium conversion of dinitrogen tetraoxide in a constant volume batch reactor. So that's the required information. Let me go back to the problem. So this is our given set of data. The data that is still to be picked from the problem, taken from the problem. I suggest that you take a picture of the sample problem. That way, when I go to the Jamboard, you still have a copy of the problem with you. We need not go back to this particular slide. Okay? So now I will go to the Jamboard. Okay, wait, class. Okay, I hope you can see the Jamboard already. Now, so as for our given, so if you have the copy of the problem with you, can you give us one given information based on the problem that you have taken the screenshot of? I'll start with the stoichiometric equation that will guide us in solving this problem. So that's our stoichiometric equation. And this is at constant temperature. Now, what else are we given in this problem? Can you give me one? Kent, Dalida?
Temperature of N2O form is at 340 K and 202.6 kilopascal.
So thank you. So you have the temperature given to be 340 K and the pressure, which is 202.6 kilopascal. Okay, we'll have another one. The other given, can you give it to me, Pilar?
Equilibrium constant means 0.1 mole decimeter.
So you have like 0.1 mole per decimeter cube. Okay, so that's our equilibrium constant. So we're just asked for the equilibrium conversion. So if we set dinitrogen tetraoxide as A, then we are asked for the equilibrium conversion of A. So that would be your XAE. Is there anything that we have missed writing down? Okay, somebody wrote in the chat box, none. Okay, actually, there's none, but this is very important. Later on, you'll see how important this is. So it was stated that this is in a constant volume batch reactor. In our next topic on variable volume batch reactor, this very information that is stated and specified is in the problem is very important, especially if we're dealing with gaseous reaction. So this is a gas reaction, and as such, this should be stated. Otherwise, we will have a different manner of solving this problem. So now we are after for the equilibrium conversion. How are we going to start solving this problem? Do you have any suggestion on how we're going to start solving this problem? We are asked for the equilibrium conversion. Anybody? What will I start with? What would be the working equation that I'll start with, if you have any idea?
Rate law, Miss.
The rate law. What you mean? The rate law, the rate equation.
Equation.
Because considering the forward and the reverse reactions. Sige. We can start with that, but since you are asked specifically for the equilibrium conversion, we need to make sure that the working equation for such we have written. So in this case, we will write for the equilibrium conversion equation first. What do you think will be our working formula in determining the equilibrium conversion? Since this is being asked, so I'd like to start with the working equation where the equilibrium conversion could be seen. So how would you start writing this particular equation, or how do you think should you write this particular equation? Which of the data that is provided in the problem could lead you to this equilibrium conversion? Okay, sige. So we'll start with the equilibrium constant. So we have discussed that the equilibrium constant is what? So I'm leading you there. The equilibrium constant is the ratio of the concentration of the product at equilibrium, right? The concentration of the product at equilibrium raised to their coefficient in the stoichiometric equation divided by the concentration of the reactants at equilibrium raised also to their coefficient in the stoichiometric equation provided. So you have here, by the way, I missed writing the two. So in this case, if I set dinitrogen tetraoxide as A and your nitrogen dioxide as B, then I can write this one as C. Concentration of B at equilibrium, it will have to be raised to 2 because of this stoichiometric number here before nitrogen dioxide. Then I write the concentration of A at equilibrium understood to be raised to 1 because its coefficient here is 1. Okay? So your equilibrium constant was written in terms of the ratio of the products raised to their coefficient in the stoichiometric equation to that of the reactants raised to their coefficient in the stoichiometric equation at equilibrium. So this is it. If you have several products here, you should do multiplication here in terms of their concentrations at equilibrium. If you have several reactants, you do the same. Now we can rewrite this particular C sub BE as C sub BO. Now, B is a product, so you will have to write it as 1 plus XBE. Now, you use plus because it's a product, and this is its equilibrium conversion. Now, since this is squared, you have to write this as squared, and this also should be squared. Your CAE will be CaO 1. Now, it's a reactant, so minus XAE. So we are actually after the this XAE here. So we have now a working equation that has the XAE because your equilibrium constant was given in the problem. Now, we will simplify further that particular formula that we have. So if we'll have CBO, this will be squared, and we'll have this expanded. So you have 1 plus 2 XBE. So the product of this times 2 plus XBE squared. Now we divide it still by CAO. And then we can write here minus CAO XAE. Okay. Now, we'll have the numerator of this particular fraction expanded. So we'll go to the next slide. Your CBO here squared will be distributed. Okay. In your numerator. So you have CBO squared plus CBO XBE. We have by 2 here. That is, you have 2XBE times CBO squared. So this should be squared. And then we have CBO squared XBE squared. Okay, that's after we have done the FOIL method here, distributing the CBO squared to these 3 terms. Your denominator would still be CAO minus CAO XAE. Okay. Now, what seems to be the problem with this particular equation that we have? What is the problem with this equation? We already have the XAE, but we of course have the problem. What is the problem here?
Wala. Ay, ang CBO, miss, wala na value.
Okay, number 1, we don't have the CBO. And we don't have the XBE. Okay, we do not know that. So we need to have an alternative formula or expression for these terms that contain these 2. That way we can solve this particular problem. Your K sub C is given to be 0.1. So I'll write it here. I'll write that as 0.1. And initially, of course, you don't have CBO, but you can determine it. So you can see that the problem gives you that if you have the problem with you, if you have taken the screenshot, it says there that the feed consists of pure dinitrogen tetraoxide at 340 Kelvin and 202.6 kPa. So you are starting with pure dinitrogen tetraoxide. So based on that particular phrase, there's a way for you to determine the CBO, which initially we do not know. Now, how do we determine the CBO in this case? Anybody who has an idea on how we determine the CBO or the initial concentration of B or of dinitrogen tetraoxide? What do we do? Okay, so assuming ideal behavior for your gaseous reaction, then we have PV is equal to nRT. So we divide this equation by BRT. So the left side would be P over RT equal to N over V. This N over V could be the concentration. So specifically, we can write based on the statement that the system is starting with pure dinitrogen tetraoxide, we can write that the initial concentration of dinitrogen tetraoxide will be solely based on the pressure that is given in the problem divided by the product of the universal gas constant and the temperature. because your pressure, the pressure of your system, is solely due to the presence of your dinitrogen tetraoxide. So based on the problem, it's given that your pressure is 202.6 kilopascal. So we write 202.6 kilopascal. Now, what R are we going to use in this case then? Since we have kilopascal and Kelvin, we will use the, what R will you use? What universal gas constant will you use in this case? Alisa, what universal gas constant are we going to use since we're given kilopascal?
8.314 Miss.
Sige, so you have 8.314. What's the units, set units for this, Alisa? So we can check for dimensional homogeneity for our CBO. What's the set unit for this?
Ng joules mole
joule.
per Kelvin.
A joule per mole Kelvin. So we could see that since you have the joule here, there's a need for us to change the kilopascal here in the numerator. So I'll just change this right away since we don't have that much space here. You can write this as times 10 raised to 3 Pascal. Okay, and then your temperature is 340 Kelvin. So in this manner, if you cancel this one, your joule will be your Newton meter. It will be taken the Pascal per square meter times meter, that would be your Newton meter. So your corresponding resulting unit for your concentration initially for CBO in this case will be what? What would be your resulting unit for CBO? Can you please solve for CBO and we will affix the corresponding final unit, set of units. GU, can you solve for CBO? And then tell the class the corresponding final set of units.
Yes, Miss. Wait lang, Miss.
Okay.
$71.67, Miss.
71.67. That's it?
Miss.
Sige. May I ask the rest to check this as well? So what would be your final set of units for the concentration of B if you're dealing with this set of units here, Gio? So ano imo final set of units? This would be then in unit for concentration in SI. Okay, so Nika wrote 71.6722 mole per cubic meter. So that's correct. So this is mole per cubic meter. Okay, now our concentration here, our rather equilibrium constant has the unit, set of units. So we're going to check its mole per decimeter cube. So there's a need for us to convert our cubic meter here to decimeter. That way we'll have dimensional homogeneity and the values that we are using. So 1 meter is equal to 10 decimeter. So we raise this to 3. Okay. So we'll have 0.07167, right? So this would be divided by 1,000 now. So this would be mole per decimeter cube. Okay, so we have the CBO now. The initial CBO that seems to be our problem here in the numerator for our equilibrium constant, we already know. Now, so there's a way for us to address the problem of the product of CBO and XBE based on the stoichiometric equation. So we go back to our stoichiometric equation and we can write this particular relationship that CaO XAE divided by 1 is equal to CBO XBE divided by 2. Why is that? Because based on our stoichiometric equation, you have 1 for the coefficient of dinitrogen tetraoxide, our A, and you have 2 for nitrogen dioxide for our B. So you can use that particular stoichiometric relationship. That way, we can have this relationship here. And from here, we could see that CBO XBE is just equal to twice of CaO XAE. Okay. And by the way, class, I'm sorry. So the problem that Bobby said a while ago regarding initial concentration of B in here, remember that our B is the product. And we're starting with the pure dinitrogen tetraoxide at the start. So instead of solving for CBO, which we cannot because we're starting with A, what we have solved in here is actually A, not B. Okay, because we have changed the identities of our species as A and B. So this is CaO, correct that one. And this is also CaO here, not CBO. Okay, so this is CaO. Because B, we don't have it initially. We only have A present initially. Okay, so we can replace the CBO XBE by 2 CaO XAE based on this particular relationship that we have. So going back to equation 1, so from 1, your K sub C is equal to. So I still write CBO squared plus. So in the case of the middle term, you will have here 2 CBO times CBO XBE because of this CBO squared. So if you can write it separately, you will have CBO or 2 CBO times 2 CBO XBE. And you have here plus. So in the case of the pure CBO XBE squared, you see this one, that would be replaced by 2 CaO XAE. And that should be also squared because it's squared there. Your denominator will be CaO minus CaO XAE. Now, we know initially that we don't have the product, so this would be 0. This could be replaced actually by 2 CaO XAE. However, the multiplier here, so this multiplier of CBO is 0. So this entire thing will be 0, just like the first term. So your second term will be all 0. So now giving you a more simplified form for our equilibrium constant. So you have 2 CaO XAE. So you can have this squared, you can also have this squared, and this becomes 4. So your 2 becomes 4. So we can cancel whatever we can cancel now. So you have 4, and we divide it. So since we need to cancel the common factor between the remaining term in the numerator and in the denominator, so we'll have here this expanded form written in its original simplified form. So we can cancel the CaO and we still have 1 left in here, giving you this particular equation 4. Now your CaO, the remaining CaO here is 0.07167, and you will have here XAE squared, and this is divided by 1 minus XAE. This expression will be equated to the equilibrium constant value, which is 0.1. Okay, based on our given. Okay, that's 0.1 mole per decimeter cube. So though Bobby suggested a while ago that we're going to write the rate equation, and it would actually lead to this if we're going to,
Excuse me.
yes.
Nag-zero ang CBO, Miss. How?
Okay. Please check your screenshot for the problem. There's a phrase there in the problem that says that your system starts with the pure dinitrogen tetroxide. So we can conclude from that particular phrase that there is no B initially present because the system starts with dinitrogen tetroxide, and this dinitrogen tetroxide is the one that is going to decompose to produce your nitrogen dioxide, which is our B. Did that answer your question, Gio?
Yes, Miss. Thank you.
Sige, sige. So can you please solve for XAE now based on this equation here at the bottom? 0.1 is equal to 4 times 0.07167 XAE squared over 1 minus XAE. You're expected to have 2 answers, but only one is acceptable. So you will have XAE equal to
0.4414, Miss.
0.44. The other one is
14. Wait, Daniel lang. Negative 0.79.
so negative 0.79. So this is not valid. So our answer would be this one. The equilibrium conversion for dinitrogen tetroxide is 0.44. Sige. Okay. So any question here? Okay man to, ang suggestion ni Bobby that we start to write the net rate equation based on this. And then we can set that rate equal to 0 at equilibrium, because at equilibrium, the net rate of formation of anything is 0. So we can equate it to 0, and actually we're just deriving this particular equation then. So we'll go straight to the primary and principal fundamental principle of equilibrium, that it is equal to the ratio of the concentrations of the products raised to its coefficient and concentration of the reactants raised to its coefficient at equilibrium. So diretso na lang tadi. Although this one came from that particular net rate equation that you're going to write. So any question here? Okay, so if there's none, I'd like to go back to our slides.
I miss.
Okay.
Kung multiple reactors, bala misaw, ano gani miss?
Again,
I-plus or
excuse me.
i-multiply?
Multiple
Or multiple
reactions. Multiple products.
Like for example, multiple products, i-plus siya miss or i-multiply?
Multiply. Let's say, for example, you have 2A plus B forming 3C plus D. Your equilibrium constant for this would be concentration of C at equilibrium raised to 3, concentration of D over concentration of A raised to 2 times concentration of B. This is all at equilibrium. So you multiply the concentrations raised to their coefficients. This could also be, if you're not given concentrations, this could also be expressed in terms of partial pressure. By the way, that's C, then partial pressure of D, partial pressure of A, partial pressure of B. all at equilibrium. That could also be your K sub C. This one we write as K sub C because we have concentrations. We can write this also as K sub P based on partial pressures. Okay, did I answer your question?
Yes, Miss. Thank you. Okay.
Sige, we go to our slides if there aren't any questions here. Okay. So we proceed. So we go to the concept of reactions of shifting orders. This is a very short discussion in Levenspiel, but this is also very important. I'd like to just show to you the slide because it cannot be projected, especially the pictures. I don't know why. So I'll just show to you the slide. So this is our next part of the slide, which is reactions of shifting order. See, if you're given this particular rate equation, this is your rate equation, and this is your rate law. If you have the R, negative R sub A written in lieu of negative dCA dt, it's equated to K sub 1 C sub A divided by 1 plus K sub 2 C sub A. At high concentration of A, or that's of C sub A, reaction is of zero order with rate constant in the form of a ratio of K sub 1 to K sub 2. So why is that? Let me annotate. Or before I annotate, does anybody know the reason why that at high concentration of A, reaction is zero order? So if this is your original rate equation, at very high concentration of A, the reaction is zero order. Would anybody know why is that?
Okay, wait.
Sige, Bob.
Duga cancel out, miss, ang C sub A sa, wait, K sub 1 over K sub 2. Duga cancel out, miss, ang concentrations ni A wala, miss, base mo na.
So why do you think, then what happened to the 1, Bob, in the denominator? So your denominator is originally 1 plus the product of K sub 2 C sub A. So what happened to the 1? Anyway, so Bobby is right, but you need to understand why the remaining expression here is simply K sub 2 C sub A. If you have very high concentration of C sub A, it's like that the product of K sub 2 C sub A is very, very high compared to 1. It's just like this one is not existing anymore. It's just like if this is 1 million and you're going to add 1 to it, that's 1 million and 1. The 1 is insignificant compared to the 1 million. So that is why you take 1 out of the picture. So Bobby is correct that what is left in the picture now is this K sub 1 over K sub 2 because the two concentration C sub A's in the numerator and denominator cancels each other. Now at low concentration, on the other hand, so this one is very low. What is left? So I'd like to clear my markings first. So at very low concentration this time, it's like 1 is very, very, very large compared to K sub 2 C sub A. If this is 0.000001, you add it to 1, it does not have any significance at all to 1. So it's like you're taking it out of the picture. So your reaction is left with K sub 1 C sub A divided by 1. So now your order shifts to first order with respect to A with a rate constant of K sub 1. That is at very low concentration. So there are cases in Levenspiel, or I think there's a problem in Levenspiel, I'm not sure, that ask you to what would be the resulting order of your reaction if you have this particular concentration. very high on this, very low on this. So you go back to the principle of how can a value be insignificant compared to another. So if it's very high or very low, then it's insignificant when compared to another value. Very high, the other value now becomes insignificant compared to it. So in the process, you get to simplify your expression. And then come up with a rate law that is just written without a denominator. So wala na siya denominator nga resulta because you get to eliminate expressions that are at times separated by either plus sign or minus sign. So this is under the topic reactions of shifting orders. Okay, so any question on this? Okay, so if there's none, we go now to what I've mentioned regarding differential analysis. So we are done with integral analysis, constant volume reactions. So before we go to variable volume reactions, this is the next topic, constant volume, but we're going to use differential analysis, not integral analysis. Now, why are we going to use differential analysis in the first place, which is going to be relying on graphical approach? If the data that is given to you is large, like probably more than 7 pairs of data, large na siya, budlay na siya integral analysis. So you resort to differential analysis. So you can use Excel to do this, but in drawing your curve, initially you have to draw it by hand. So you could see that on your slide that the first thing that you're going to do, given the pair of concentration and time data, so gintagaan kasang, for example, the problem gives you something like this. You have CA and you have D, none. So what you're going to do, you plot C sub A versus T. Okay, then what do you do next is this. Hindi siya so we'll have to eliminate it first. Then by eye or by hand, you have to draw a smooth curve to represent your data. Now take note that the curve need not pass. So it need not pass through all the experimental points. So meaning it's just like the best fit line. You're going to draw the best fit curve on the points that you have plotted. Points resulting from plotting C sub A versus T. So by eye or by hand. Okay, it's important that the curve that you're going to draw is not something like this. No, you're going to draw a smooth curve, the best fit curve that you could draw based on the C sub A versus T data that you have plotted. Then what you're going to do next is this. That's not the end of the graphical process, but you are to determine the slope, which will represent the rate of change of the concentration of A versus T, or the R sub A of this curve at selected concentration values. What does this mean? For example, I'll draw here. And let's say you have these points. Okay, these are your data points. 1, 2, 3, 4, 5, 6, 7. Damuon tabi. Here. And let's say you have one extraneous point there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So you have 10 points. I have one here, another here. So these are your C sub A versus T data. Okay, now second instruction is you draw by hand. So we draw by hand. The best fit curve that we can draw. So I'll just draw. Okay, we'll make it a different color. I'll draw here my best fit curve. So this is my best fit curve. It could be different compared to yours. So it could be something like that. That's my best fit curve in my best judgment. Now, According to step 3 here, you're going to select concentration values. And based on those concentration values on your curve, you are to determine the slope. What does this mean? Kita talaing a color. So this one. Now let's say I'll choose this concentration value here. So I have one here. I have one there. I have one here. The more points you select, the better, because you will have more dCA dt values. So you have selected 4 points here. I'd like to draw separately my curve now because it's small there. So I like to draw it here. Naindiga mo. Then I'll have here my points. Let's say I'll just select 0.1, and that 0.1 is this. I want to show you 0.1. So that point is here. This is my 0.1. So this is my 0.1. What I'll do is I'll draw a line that is tangential to my curve on this point that I have chosen. This is 0.1 corresponding to a certain concentration, for example, which is concentration 1. So I'll draw a tangential line on this point that I have chosen. This is the tangential line I've chosen. That tangential line is actually having a slope. This tangential line has a slope which is equal to dCA dt, or that's negative dCA dt because this is negative slope. That would be my negative dCA dt, the slope of this line. How do I get the value of the slope of that line? So I will again draw my line. The line that I've drawn here, I'll place it here. For example, I have already CA, right? May CA1 ako de. I have CA1. I'll get the time for that. So that would be my T1. On this line that I have drawn, that is tangential to 0.1, I'll choose another point. Then that would be, let's say, CA2, whatever that CA2 is. And I'll get the time here. So I now get the slope of this line. So the slope of that line, which is dCA dt, is equal to CA2 minus CA1 over T1 minus T2. So CA2 minus CA1 over, CA2, it's also 2 because it started with 2 over CA1. So you'll get a slope which is negative. True, because in here, you really have a negative rate of change. So the answer that you'll be getting here is negative. Now you'll get that slope. So you have now data of dCA dt, or that would be the negative rate, and you have it together with concentration that you have chosen. Okay, so if you have a piece of paper there, you write that with these 4 concentration points that you have chosen on the curve that you have drawn, you will have 4 sets of data. 4 sets of data pairs. Specifically, what are those data pairs? CA, the chosen CA, and the corresponding slope of the line tangential to your best fit curve written or drawn on that particular point. So ang imo data point is pairs are RA versus CA. So you have data points. So this will constitute 4 data points. The more data points or the more CA values you have chosen, the better is your approximation of the rate equation of your set of data, the set of data that is provided in the problem. Okay? Now, before I go to the next direction there, any question in here so far as to the procedure for differential analysis? So wala man. Sige, so good. Plot C sub A versus T. Draw the best fit curve that you have on those points. Select concentration values on the best fit curve and determine the slope of that tangential line on this chosen concentration points, and write your set of data in the form of rate versus C sub A. Okay? Now, if there aren't any questions, then I will clear all the markings here to see what would be the next thing that you're going to do. Oh, done. Sige. So I'll close my drawings here. So the next thing that you're going to do is this. Plot LNCA versus LNRA. The linearized nth order form of the rate law together with the equation of the best fit line will give the order of the reaction and the specific reaction rate. Okay. Can you please take a picture of this set of procedures so I can go to the Jamboard and explain this number 4. Plot LNCA versus LNRA. The linearized nth order form of the rate law together with the equation of the best fit line will give the order of the reaction and the specific reaction rate constant. So please take a picture of that so I can go to the Jamboard and show how it's done. Okay, so I think you have taken the picture already. We go to our Jamboard. Okay, so you use the next page here. Now, remember, a while ago I said, just use a different one. You will have, let's say, based on the 4 values that you will have, you have the rate and you have the CA. So you have 4 here, 4 pairs of data based on the example that I have given to you. Okay, now what are you going to do with this? Before I explain about the plotting of the ln of CA versus the ln of RA, remember that your rate law, okay, your rate law is generally written in this form, right? With the C, with the K and the N as unknowns. You don't know this. But if you linearize this equation, you linearize, you take the ln of both sides. You have ln of K C sub A raised to N. And based on the properties of ln, you will have it something like this. And you will have ln, the rate equal to, I'll rearrange, this n can be written before here. So you will have it as n ln of CA plus ln of K. Okay, after doing linearization, this, you will notice that this becomes your Y, this becomes your X, and this is your Y-intercept, and this is your slope. So your road data, based on the 2 graphical steps that you have done, drawing the best fit curve and drawing the tangential line on the chosen concentration points, you will have this raw set of data again. So after you have done that, you get the ln of this. So you get the ln of the rate, ln of the CA. So in the process, you'll also have another 4 set of data. The ln of the rate is your Y. That's your Y. The ln of the CA will be your X. You can use your calculators in the stat mode and then get the best fit line equation. Now, based on the best fit line equation, or you can do this properly on Excel, you'll get the slope of the line, which is directly will give you the order of the reaction. And then the y-intercept of the line is your ln of K. If you make that as the equation of your E, then you will be able to get the very important rate constant. Then knowing the N and the K, you go back to this general form of your rate law wherein the K and the N are not known. And that's how you find the rate law for the given empirical set of data. That's your differential analysis for constant volume batch reactor data. Any question?
None so far, Miss.
Sige. So clear man sa iban. So you're going to do differential analysis. It's actually the mix. It's a mix of graphical and analytical approach. Hindi siya purely analytical, hindi man siya purely graphical. But I think 65 to 70% graphical gid siya. Okay? It's the way you interpret your empirical set of data for constant volume batch reactor data. If it's variable volume, you also have differential analysis, but with a different set of equation, and it's seldom being used anymore. Okay? So any question here? No question so far, because this would be the end of constant volume interpretation for batch reactor data. So we will go, the second part is variable volume batch reactor data. Again, we'll have integral and differential analysis there, but it's just short because the equations are already given and pre-derived and given for you to use. So no question here. Okay, I'll stop momentarily. I'd like to go to Levenspiel to give us, to select problems that we can solve. Application of what we just discussed. Especially on multiple reactions with gas. So in this particular problem, you're given an elementary two-step series reaction. Now, this is different than the one that was derived by Levenspiel, because in here, your rate constants are equal. Now, in that particular set of formula, in which we have formulas for maximum concentration of the intermediate, the time when it is reached, that's on the premise that your K sub 1 and K sub 2 are not equal. So in this case, we will have another derivation as to how we're going to answer this particular problem. So you're asked here to find the maximum concentration of R and the corresponding time that this occurs. Given that you're starting only with an initial concentration of A, no intermediate R, and no final product S is present, your rate constants are equal. Okay, so far our given is so short. So this will be a problem which is solely relying on derivation of formula that you can use. Once you have already the formula for this scenario, you can also use that same formula when such a scenario again you encounter, wherein K sub 1 and K sub 2 are equal. Okay, so let me go to the Jamboard and okay, sorry. We'll try to solve this problem. That's 3.15. Wait, class. So I hope it's not in the problem set. Check ko class. Wait, ha. Okay, it's not in the problem set. So I'm referring to the problem set. Okay, where is the jam? So this is our given. A forming the intermediate R and forming the final product S. You have K1 and K2. K1 and K2 are equal. CaO you have, but CRO and CSO are both 0 initially. So this is at time equal to 0. Okay. So we will still derive just like what was done during the discussion in class. So you set up your rate equation for this. So you will have rate 1 dCA dt is equal to K1 CA. So that's the rate of change of the concentration of A. So we can get rid of that one there. Then you have dCA over CA is equal to K1 dt. If you will integrate, you start with CaO and happen there. You have here CaO and you have here Ca0 to T. We have done this in class so just as an exercise for mastery. So you have negative ln of Ca over CaO and you have K1 T. So you will have to raise both sides to E. So you will have transfer the negative first on the other side. So you will have Ca over CaO is negative K sub 1 T. And E, or rather, if you raise everything to E, you already have the E in here. Or better yet, you have here ln of Ca negative K sub 1, K sub 2. Then we raise everything to E. So you have Ca over CaO is equal to E raised to negative K sub 1 T. Your Ca is equal to CaO E raised to negative K sub 1 T. This still holds true. This formula allows you to solve for C sub A at any particular time T. Now we go to the intermediate R. So dCr dt is equal to K sub 1 C sub A. Okay, for this, and in here, you will have it negative because it's reactant already. Minus K sub 2 C sub R. We transfer this on the left side. You have dCr dt plus K sub 2 C sub R, and you will have K sub 1 C sub A, which you can change based on this one, based on that one. Your Ca can be written as K sub 1 CaO E raised to negative K sub 1 T. Okay, your linear DE in this sense would be something like this. Okay, that's your linear DE. Now, based on what you have learned in DE, you are to determine the integrating factor. And the integrating factor is based on this one. Okay, the coefficient of your unknown function. We're so used to seeing this in DE as dy. So if you're going to compare this to the DE then that you have, this is your dy dt plus p of x or dy dx. We'll have it na lang dy dx. So dy dx plus p of xy equal to q of x. So that's the form that we have. Everything here on this side is a function of the independent variable time, and our independent variable here is x. The second term on the left is the product of an expression in terms of the independent variable x. In this case, it's just a constant, and the unknown function y. Our unknown function here is c sub r. Okay, and this is our derivative c sub r or dc sub r dt equal to the dy dx. So if we'll use this particular comparison to our dE here, so our mu based on our formula is e raised to the integral of k sub 2 dt. Wait, is it k sub 2? Yeah, k sub 2. And instead of dx, you will have dt. So you will have e raised to k sub 2 t. So the answer to this particular linear DE then would be your unknown function. In this case, your unknown function is C sub r. You multiply it to the mu, which is e raised to k sub 2t. And you're going to integrate it with respect to the entire expression of your q of x. So you have k sub 1 CAO e raised to k sub 1 t. That's negative. That's your entire q of x here. K sub 1 CAO e raised to negative k sub 1 t. And you're going to multiply it with the integrating factor e raised to k sub 2 t dt. Okay. Now with k sub 1 and k sub 2 being equal, what happens to these two? This becomes e raised to 0 because your k sub 1 t minus k sub 2 t with the 2 equal will become e raised to 0. So you even have your CR e raised to k sub 2 t. You even have a more simplified integral here to deal. So you have k1 CAO because this one would be e raised to 0 and that's 1 dt, which will give you k sub 1 CAO t plus a constant of integration, which we'll just label as C prime to make it different than the C's that we have here. So I'll rewrite that expression. C sub r e raised to k sub 2 t is equal to k sub 1 CAO t plus the C prime. How do we find the C prime? Anybody who has a suggestion? How do we find the constant of integration C prime?
Wala kamis may i-input ayhan nga data para like siya na lang pala mabili, no?
So gamiton to ang condition that at time equal to 0, we don't have CRO. So it was given in the condition that initially you only start with A. You don't have this 2. So we use that as a condition to find the C prime. So if we substitute it in here, this will be 0 times e raised to 0, which is 1, is equal to, so you will have k sub 1 CAO. That would also be 0 plus C prime. Therefore, C prime is equal to 0. So your C sub R then is equal to k sub 1 CAO. I'll transfer this on the other side. So you will have e raised to negative k sub 2 t. See this one negative, kay ara siya sa dalom t. Right? That's your C sub R k sub 1 CAO e raised to negative k sub 2 t multiplied to t. But we haven't answered yet the question. The question is, based on what you have taken there as a picture, determine the maximum concentration of R and when does this happen? So you have now a formula for C sub R. How are you going to determine that maximum concentration? You have that as a tool already before. How do you find the maximum concentration of R? And how do you find the time of that maximum concentration?
Kung maximum concentration, wait, hindi. Kung si A miss 0 na,
Si CAO, hindi gina siya mag-0 ang initial concentration kaya amo na siya gani ang ara lang. Wala ta intermediate, wala ta final product. So we have to start with the species nga kinahanglan ta i-convert to the final product S. So hindi gina siya mag-0. Karon wala na ta i-derive eh. There's no point in what we're doing here if it's 0. So I'll go back to that again to refresh your memory. You have that particular tool you've learned already in the past on how to get the maximum concentration, maximum value, minimum value of anything. What is that? Determining the maximum or minimum value of anything. And it's really very, very useful. What is that? Ipat naman sila. Maxima, minima, gyapon. You use maxima, minima from your EMA 101. So you get the derivative of the concentration of the intermediate R with respect to T. So you have T's here, in the product of this exponential function and this T, and this one is a constant. So you can perform product rule of differentiation to these two. The first term times the derivative of the second plus the second term times the derivative of the first. T, so you have k sub 2t times negative k sub 2. Do you follow what we're doing here? Maxima, minima. And then according to that, at maximum C sub R, dCr dt is equal to 0. So we zero the left side. So 0 is equal to, now if I'll have this 0, this could be placed in here. So that would also be 0, right? So this negative that I have, I'll place here on the left. So k sub 2t, I'll write it as positive. Hindi na lang. Okay, nabutang pa ko gali 0. K sub 2, negative k sub 2, t e raised to negative k sub 2t plus, I just wrote this first, this one. E raised to negative k sub 2t. So k sub 2t e raised to negative k sub 2t is equal to e raised to negative k sub 2t. This cancels. So you have k sub 2t is equal to 1. That time, not T max, but rather one over k sub 2 or 1 over k sub 1. Or it could be 1 over k sub 1 time when C sub R is maximum. So this is your working equation. Very, very easy. When the two rate constants in a particular two consecutive irreversible reaction in series are equal, the time when the intermediate R concentration is maximum is the reciprocal of any of the two rate constants. As to what would be that concentration, you go back to your formula, this one, this is your formula, and substitute the T for maximum concentration. So you'll have K sub 1 CaO E raised to negative K sub 1. Wait. K sub 1 CaO E raised to negative K sub 1 or K sub 2 just the same because they are equal. You're going to multiply it to T. And this T is 1 over K sub 1. And you're going to multiply this entire expression by 1 over K sub 1. So your maximum concentration then is equal to, this consists this cancels. So that would be CaO E raised to negative 1. Do you have any questions? Do you all get it?
Yes, miss. Medyo. Review lang naman.
Okay, review. Reviewon lang ninyo. Sige. So, hapos-hapos ng sang iya nga time when C sub R is maximum. And you have this as the maximum concentration of the intermediate R. So, actually, your primary tool here is your differential equations. Okay? Sige. We'll choose another problem from Levenspiel. If there aren't any questions here anymore. Okay, that's for reversible. No, sorry. We have reversible, we have series. This one class, the 3.15 is actually homogeneous catalyzed reaction. However, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This is differential analysis. So, lawig siya. So, we can also do integral analysis for this, but it's suggested that once you have a lot of data points already, that should be differential analysis. And it is Michaelis-Menten. This is its rate equation. Differential method. Okay. So we can start would you want this one, or we can go to a problem that has parallel reactions? Parallel reactions there. Okay, snake eyes magbo is not parallel. Variable volume na siya. Okay, so I'll have here that thing about Bitan 100 Bashpi. Can you see Levenspiel?
Yes, miss.
Yes, miss.
Sige. We can use this particular gaming problem to illustrate parallel reactions. I think this is not part of the wait class of the problem set. I'll just check. 13, so it's not part. Wait lang. I have so many things to click. Okay. Can you see problem 3.13, Levenspiel?
Yes, miss.
Sige. So in this problem, you are to apply what you've learned in parallel competing reactions on a gaming problem. So Bitan 100 Bashby likes to play the gaming tables for relaxation. He does not expect to win, and he doesn't. Funny, no? So he picks games in which losses are a given small fraction of the money bet. He plays steadily without a break, and the sizes of his bets are proportional to the money he has. If at galloping dominoes, it's a game. it takes him 4 hours to lose half of his money, and it takes him 2 hours to lose half of his money at Chak-a-Lak, so another game, how long can he play both games simultaneously if he starts with $1,000 and quits when he has $10 left, which is just enough for a quick nip and a car fare home? Okay, so a gaming problem where we could apply parallel reactions, the principle on parallel or competing reactions. Can you please get a screenshot of the problem so you would know? We will not go back later to this copy of Levenspiel. Okay? Sige. Okay, now I'll go to Jamboard. Nadula ang akong Jamboard class. Wait, where is it? Dula siya. Yes, ha? Okay. Okay. Share again. Okay, here we go. Okay, next slide. Now, given what can you get out of the problem? Can you give me a given that can we write something based on the gaming problem that is comparable to that of parallel reaction? First sentence, Bitan Hundred Bashby likes to play the gaming tables for relaxation. Nothing to get from there. Next sentence, he does not expect to win and he doesn't. So he picks games in which losses are a small fraction of the money bet. So he just wants to relax and he intends to lose every time and he doesn't really win. So he picks a game, since he doesn't win, he picks a game in which he only loses a small fraction of his bet. So that's what it meant here for the first two sentences. Third sentence, he plays steadily without a break, and the sizes of his bets are proportional to the money he has. So he bets proportional to the money he has. If dako iya kwarta, dako man iya bet. Kung gamay na lang iya kwarta bilhin, gamay naman iya bet. Okay? Now, what can you get out of this? He plays steadily without a break, and his sizes of bets are proportional to the money he has. The sizes of his bets are proportional to the money he has. Now, fourth sentence, if at galloping dominoes, it takes him 4 hours to lose half of his money. So let's say at GP, how would you write this down? It takes him 4 hours to lose half of his money. How would you write that down?
Half-life is equals to 4 hours, miss.
So for galloping dominoes, we can write here, half-life is equal to 4 hours. Okay, sige, that's correct, Bobby. Next, ano ang next na statement? It takes him 2 hours to lose half of his money at Chak-a-Lak. Chak-a-Lak. Japon. Only that, at Chak-a-Lak, mas dasig iya nga dasig iya ginaperde tunga sa iya kwarta. 2 hours lang tunga na dayon. Sa galloping dominoes, 4 hours pa. Okay? Samo na siya. So half-lives, the concept of half-lives. Then what do we have here? How long can he play both games simultaneously? So he starts with $1,000. So we can write this $1,000 as CAO, for example. We'll have it as 1,000. We'll not just write the dollar sign anymore. We'll just compare it to that of an initial concentration. And he quits when he has $10 left. So ano ni siyang si $10? Yvette, what is the $10? Comparable to what? Yvette, ara kada. Namahaw, guro si Yvette. Oh. CA. Sige. CA. 10. Correct. How long can he play both games simultaneously? Required. T for simultaneous playing of galloping dominoes. Mali-mali, naging kuya. Galloping dominoes, GP. That's your GD. Galloping dominoes. And shock alarm. Okay. Would you like to add anything here? May given pa na wala nato na sulat or everything is there already? Everything there? Sige. So we write the solution here. Next slide. So let's say the initial money he has is A. Okay. He plays both games simultaneously this time. So comparable to a parallel reaction. So we'll have here G for galloping dominoes and chakalak C. So I will have here K1 and K2. Okay, so that's our parallel reaction. Then how are you going to use these two particular information given in the problem? Wait, class. This one, the two half-lives. How are you going to make use of this? Two information. Half-life of his money at galloping dominoes is 4. Half-life of his money in chakalak is 2. How are you going to make use of these two information?
Makuha mo, miss, ang value ni K1 kag ni K2.
Okay. So
Okay.
how are you
May
going to
convert.
get the, okay, you're going to get, or you're going to write first the rate in terms of just one game he plays. And that's your K1 CA. Let's say this is for galloping dominoes. And your DCA DT equal to K sub 2 C sub A gyapon will be for chakalak. Do you all agree that your half-lives will be used, the given half-lives will be used to have the two rate constants? If you're going to write your net rate equation, it's for the parallel reaction, DCA dt is equal to K sub 1 C sub A plus K sub 2 C sub A. Okay? K sub 1 C sub A, K sub 2 C sub A. Common C sub A, so you will have K sub 1 plus K sub 2. Then you will have this C sub A. Then what we do? Negative DCA over CA is equal to, I'm writing this one. We have derived this actually. I'll transfer it here. Then you'll have here, sorry. I can't see anymore. I'll just share again, class. I click the, okay. Nag-a-appear siya. Wait, class ha. Okay, tara na. K sub 1 plus K sub 2 dt. So you start with CAO and you end with CA 0 to T. So you have negative ln of CA over CAO is equal to K1 plus K2 times T. I'm working on the equation that we have set up for our simultaneous reaction. Okay, parallel competing reaction. So we'll place here negative ln of your CA is $10, your CAO is $1,000, and it's equal to K1 plus K2 times the T. Can you please solve this one? The negative ln of 10 over 1,000.
4.6052, Miss.
4.6052 times 10.
Wala na, Miss. Amo lang na.
Okay. Okay. So this is equal to K1 plus K2 times T. So this is our first working equation. You get to know this time. This is the time that we're after, this one, if you know already the K1 and the K2. So just like the suggestion of Bobby, so you go to the next slide. Negative dCA dt is equal to K1 CA. This is for galloping dominoes. And it's like a first order reaction. So you will have negative dCA over CA is K1 dt. And you will have here CAO, CA. This is when the game is just played one at a time. You have ln of CA over CAO. Negative is equal to negative K sub 1 T. If you're going to use the concept of the half-life, pwede man, mas diretso. So you can place here negative ln of 0.5 CAO during half-life, and you have CAO is equal to negative K sub 1 times the time, which is 4 hours in the case of galloping dominoes. So you'll have K sub 1. You do the same for Chak-alak. So I'll go straight here for Chak-alak. It's the same pattern as that one. So ln of 0.5 CAO over CAO is equal to K sub 2. But this time, why did I place negative here, class? Wala na siya negative. I-adding negative sa pihak. So you'll have here, time here is 2 hours. So you will have corresponding values for K1 and K2. Okay, what's our value for K1 and K2? Okay, 0.1733. This is per hour. K2. T466 per hour. Okay. So we can have 0.1733 here. 4.6052 is equal to 0.1733 plus 3466. 0.3466. So the sum of these two should be multiplied to T. So T is 8.8578 hours. So if he's going to use his $1,000 and just have $10 left, he can play for more or less 9 hours. I don't know how he's going to do that because he's going to play both games simultaneously. Okay, but this is the time it would take him to lose $990 for him to relax. Mayaman siya no makarelax siya kakaperde sa $990. Anyway, so any questions here? On Thursday class, I'll give you one example. I'd like to go back to Levenspiel, where we have differential analysis together with homogeneous catalyzed reaction, the one I've shown to you a while ago. Okay, it's hard to show it in here where I'm writing on that. This one, 3.15. So at room temperature, sucrose is hydrolyzed by the catalytic action of enzyme sucrase as follows. Starting with a sucrose concentration of 1 millimole per liter and an enzymatic concentration of 0.01 millimole per liter. Your kinetic data is given here, obtained from a batch reaction, a reactor rather, and you are to determine whether this data can reasonably be fitted by a kinetic equation of Michaelis-Menten type. So in your biochemical engineering, you're going to study in detail biochemical reactions, enzymatic reaction, and this particular rate equation is common to it, the Michaelis-Menten type of equation. So if this fit is reasonable, evaluate. So if the data fits this particular rate equation, you are to give the value of K3 or K sub 3 and C sub M. So we're going to solve it using integral analysis, then we'll repeat it using differential analysis. That we will do on Thursday before we proceed to, so go back to the slide. So on the slide, after differential analysis, so that's your differential analysis, we'll have varying volume batch reactor. So we have this varying volume concepts. Okay, this one, okay, basta gani, may equation, class hindi siya kitanon. So you have these equations, okay, ready-made equations, and then we go to differential analysis. And that's the end for the entire interpretation of batch reactor data. So I think Thursday, we can start with a portion only. We'll finish it on next week. But next week, you will have a quiz on kinetics on Tuesday. We will switch again the schedule for SEPA and kinetics on Tuesday next week. Okay, on Thursday, you will have a quiz on SEPA on the application of determining the condenser and reboiler duties. Okay? Do tayo na lang the time that we have, which is 2 weeks left, 2 weeks more is more than enough. Any questions? Any point